Dear students, today we are solving the ISI M.Tech CS 2024 sample paper, and this is the part B, which is for the computer science students. So we have a question here. Let's have a look into it. So consider the two binary search trees BSTs named T1, T2, and the root 1 and root 2 respectively. Both T1 and T2 are AVL, that is Adelson Velsky Landis trees, and n greater than 0 and n greater than 0 nodes. And every node of T1 and T2 has three fields: value, left link, and right link. So define margin of the BST T2 with a BST T1 as a process that combines the two BSTs to the single BST, attaching the root of T2 and to the left of the link of this thing. So create the two AVL trees TA and TB with 7 integer and 6 integer values such that TB cannot be merged in that way. Okay, so in this case, to create the two AVL trees of this thing such that TB cannot be merged with TA. Well, TA, as per the given definition, we need to ensure that TB cannot be attached to any free left link or right link of TA. Left or right link of TA. Okay, so one way to construct such trees is to make TA a complete AVL trees with TA. Is a complete AVL trees with obviously 6 nodes, and TB with a complete AVL needs with 7 nodes. Okay, so example, TA equal to maybe 3 2 5 1 4 6, and TB is 10 8 12 7 9 11 13. So in this case, TA is a complete AVL tree with 6 nodes, and TB is a complete AVL tree with 7 nodes. Since all the nodes in TA have 2 children, and there is no free left link or right link available to attach to the root of this TB. Additionally, the values in TB are distinct from the TA, satisfying the condition, and that's the end of first part. So now let's get into the second. Design an algorithm for that takes T AVL trees T1 and T2 and input merges T2 and T1. If possible, otherwise report an error. Explain your algorithm. Deduce the time complexity of this thing as well. So traverse T1 in order to store the values in a list in L1. Okay, and T2 in order to store the values in list 2. Okay, so in this case, check if values in the L2, we need to check if any values in the L2 is already present in L1 or not. If yes, report an error. Yes, then error. If no, then make it clear. So if no common values is there, then find the minimum value in L2. So the traverse T1 to find the first node and the value, then we can proceed to the minimum value. And if n has a left child attached to the root of the T2 to the right link of the rightmost node of the left subtree of n, otherwise attach a root of T2 to the left link of n. Okay, and return the merge tree. The explanation is step 1 and 2 here is created as a list of the values of the T1, T2 respectively. The next steps are on the basis of the merging the values. Okay, and then finding the minimizational structure and find the appropriate node for node n for T1 and also for T2, and return as merge tree. So, and they've also asked us the time complexity. So traversing T1 and T2 in order to make it as take O, that is m plus n time. M and n are the numbers attached to T1 and T2 respectively, and check the common values O of m plus n time the worst case, and finding the minimum value in L2 takes 0 n time. Okay, and traversing T1 to find out n takes om time in the worst case. and attaching the root of T2 takes O log m time in worst case, and overall time complexity is log n. So the maximum height of the March tree is the max height T1 and T2 plus 1, that is for the root of the March tree. Let H1 and H2 be the height of T1 and T2. So the maximum height of the March tree is max of H1 comma H2 plus 1. So this is the end of this first question. In the next video we will solve from 2.